We introduced the concept of holonomy, which connects and provides a link between 2 points along a curve. In particular, we will start with the so-called connection that we will call capital gamma sub A, and this connection tells us how a spinor chi with the two components chi1 and chi2 transpose, so this is actually a column vector. When this spinor is parallel transported along a curve, which is parametrized by the variable s. And let me write down the equation for parallel transport of a spinor. So we have the derivative with respect to the variable s of the spinor chi, and here we have a curve gamma of s. So this curve is gamma and it is parameterized by the parameter s. And similarly to general relativity, when we take the derivative of a vector, so in the case of general relativity, we take the derivative of a vector, and that derivative along a curve is proportional to the so-called Christoffel symbol, which is the connection in general relativity. Here, we are going to set this equal to the connection gamma A, which is different from the one that we have in general relativity, but it is proportional to that. So we have I, the imaginary unit, gamma dot of A of S, so this is actually a superscript, the superscript A, so we have to sum over A, because here we have gamma A of lowercase gamma of S, and then here we have the spinor chi of gamma of S. This is the differential equation of parallel transport of a spinor, and we can integrate this. So at first, let me write down the result. Then I also want to point out or highlight how you can derive the result. So this spinor chi of gamma of S overlined, so I'm going to put this bar, and I'm going to call this S overlined. This is equal to the path ordering. So here I'm going to put a P to denote the fact that we are going to path order the quantity that's going to be put in here, and I will also explain what path ordering means. But here we have the exponential of the imaginary unit I, and then we have an integral from S underlined, so this is another point, S underlined, and the integral goes from this to S overlined ds gamma dot A of S uppercase gamma sub A of gamma of S. Then let me close the bracket, the square bracket for the exponential. Then I close the bracket for the path ordering, and then I have the spinor chi of gamma of S underlined like this. Now, path ordering means something similar to what you might have seen in quantum field theory for time ordering. In particular, it means this. So if we path order the following quantity, gamma A of lowercase gamma of S1, gamma B of lowercase gamma of S2, this is equal to gamma B of lowercase gamma of S2. Remember that these are operators. These have to be treated as operators in general, so they're not really scalars, because here we have a spinor, so it makes sense to think that this object in front will be some kind of matrix. So it's an operator. It's to be treated as an operator. Here we have gamma A, lowercase a, of gamma of S1. And this is true if S2 is greater than S1. and so on. So you can get the idea. If S1 is greater than S2, this would be the opposite. So you have to change the order here. The one that contains the smallest quantity comes on the right. Now, this object here that I'm framing right now is also denoted as lowercase h gamma of S overlined S underlined, and it is called the holonomy. It is referred to as the holonomy. The holonomy is the basic variable used in loop quantum gravity formulation. Now let me show you how you can prove this result starting from the differential equation here. I will just give you the hints and the most important comments of how to derive it without getting bogged down in the details. Now, if you consider this differential equation and you integrate it first between a certain interval, and you consider the interval to be very small, so you are going to integrate it between 2 points, say between S underlined and another point S1, S1 being very close to S underlined. So this is just an assumption. And if you integrate that expression, you get something like this. So you have chi of gamma of S1 is approximately equal to, you have the identity plus I integral from S underlined to S1 ds gamma dot A of S gamma A of gamma of S, and then you act on chi of gamma of S underlined like this. And you can iterate the procedure because now you can integrate the differential equation between another interval from S1 to S2, where S2 is very close to S1. So you get the idea. And if you iterate the procedure and you use all these formulas, well, from S1 to S2, you get a very similar formula to this one. But then you can replace chi of gamma of S1 in the formula that you obtain from here, and so on. If you iterate the procedure several times, you can write something like this. Chi of gamma of S overlined equal to the identity plus summation over n greater than or equal to 1, I to the power n, integral from S underlined S overlined dsn, integral from S underlined to Sn dsn minus 1, integral from S underlined to S2 ds1. And this series of integrals is going to be acting on the following integrand. You have gamma dot an of Sn, capital gamma of an, gamma of Sn, then let me write it here, gamma dot a1 S1, capital gamma of a1, gamma, lowercase gamma of S1, and then here we have chi of gamma of S underlined. Now, if we use the path ordering notation, path ordering of gamma AI1, gamma of SI1, gamma AIK, IK, gamma of SIK, This is equal to gamma of A1, gamma of S1, dot dot dot, all the way up to gamma AK, gamma of SK, and this is true if S1 is greater than or equal to S2, greater than or equal to dot dot dot, greater than or equal to SK, where I1, I2, dot dot dot, IK here are a permutation of 1, 2, 3, dot dot dot, K. So don't get confused when you see this kind of notation here. This I1 can take all the values from 1 to K. Once we have defined path ordering like this, we can write down the final expression for chi of gamma of S overlined. So from this and this, we can write chi of gamma of S overlined equal to path ordering of summation over n greater than or equal to 0. Now here I'm putting 0 because I'm putting this 1 inside the summation. So when you set n equal to 0, you get 1. And here you have I to the power n divided by n factorial. And then you have integral from S underlined to S overlined ds gamma dot A of S gamma sub A of lowercase gamma of S, and this is raised to the power n chi of gamma of S underlined. Now n factorial here has a meaning, so it makes sense because it corresponds to the n factorial possible permutations of the indices 1, 2, 3, 4, 5, all the way up to n. And this will lead to the expression of the holonomy that we have already seen here with the exponential.